Hello everyone, this is Sheikh John Saida from C section. Today my ADE topic is the digital circuits for mobile computing, optimizing power performance and innovation opportunities. Let us go through the topics. The introduction, adaptive techniques for power performance optimization, shipping power through a strong power delivery network. I feel the need of speed clocking. Standard cell and embedded SRAM, SRAM, observed food chain, circuits, system software, humanities. Let us go through the topic. First one is introduction. Today, mobile phones has millions of times more computing power than all the NASA computers that puts two astronauts on the moon. It is to the progress made the Moore law and the ability of software engineers to take advantages of increased computing to create new applications that help our daily life be more efficient. There is enough computational power available that we are the device of intelligence robot oriented autonomous vehicles and machine learning for smart home environment and life. Putting all this computing into an increasingly smaller factor and limited energy source creates innovation opportunities. For our industry, we can clock process at 5 GHz, but we can't use them because of the terminal limits of user putting the device in their pockets. We can drive more performance through multi-core and parallelism, but the user prefers to charge their mobile once per day. To ship millions of ICs per day means adding margin for re- reliable, resulting in waste powers and performance. New innovation to provide the automation power and performance of these devices. Next topic is adaptive techniques for power or performance optimization. Uh, on a given wafer, there is a large variation of maximum central process unit (CPU) speed of each IC due to process variation. However, at the product level, we need to guarantee a minimum CPU speed with each IC will work over all possible temperatures and variations due to the environment that the process could encounter. In the design closure state, we will sign off at the worst condition of silicon speed, voltage, temperature, and device lifetime. But in reality, this is also the worst case and cost power overhead to achieve the speed target. Therefore, by employing adaptive techniques, we can reduce this power overhead by operating the IC. The CPU to detect when operating conditions have changed. This adaptive technology allows the device to use available voltage margin to boost performance or low power consumption when possible. A smaller controller monitors the detector data dynamically, trimming the device for DC voltage bias and temperature adjustment as the device is exposed to different conditions. The result is 20% megahertz boost or 30 power saving depend on the system on chip, SOS system on chip. Operating condition. Let us use this picture and the computing subsystem. In this we have CPU, date, temperature, CPU 1, another one there is CPU 0, 1, and shader 1, shader 2, system power manager, PTP, controller, and PMIC. Shipping power through straw power delivery network. Powering the processor is also a very important consideration, and the design of power delivery network (PDN) power delivery network impact the performance capability because a very robust PDN is also associated with a higher cost. There is a very careful trade-off between the cost of the PDN solution versus the performance achieved by the processor that needs to be considered. During runtime, the processor switch between light and heavy workload continuously, causing voltage drop in the PDN. These drops they diminish the voltage margin available and compromises CPU operating speed. To minimize voltage drops, the remote sensing technology is employed, a feedback line using a print circuit board (PCB). Tracing the location closest to CPU power pins provides actual CPU voltage to the power management (PMIC). The voltage delivery from PMIC continuously com- compensates for any losses through power delivery to the processor is guaranteed to within a known error margin. The feedback margin is continuous through power supplied is constantly tracked and adjusted during operations. Figure 4 shows an oscilloscope plots before and after remote sense are enabled achieve 18 MV direct current and 11 MV AC alternate current power supply compensation. I feel the need and the near speed clocking. A structured clock mesh is often used to high clock rate CPU minimize clock inception delay and end power point secure. In the CPU, a fishbone structure is constructed to propagate the main clock to a grid of 229 tap points across the CPU. The fishbone utilizes an disturbed driver column tied to the horizontal spines. No additional vertical strapping is used, eliminating half of the traditional mesh capacitance. The resistance capacitance (RC) of each spine of uh, constrained by using tap points buffer at each grid points, minimizing capacitance and RC variations each time. A traditional clocking tree synthesis (CTS) is used to connect from the top points to lower level gates, allowing skew to as required. A direct connection to a large number of clocking tree elements maximize the potential benefits of mesh style of clock grid. To achieve this, the first level functional clock gates uh, installed in the registered transfer level are logically combined into a second level. This increases the number of first level clock loads from 3 to 3009, which are immediately behind 2009 to 229 tap point buffer. The overall CPU clock instruction delay is reduced by 35 while maintaining parity power with the traditional CTS in a 28 nm CPU design. Let us see this picture CPU bonding box, fishbone spine, fishbone reps, tap point buffer, first level clock gate, standard cell and embed SRAM. Once the CPU specializations and architecture are defined, the next step is to implement them into digital logic and implement the place and route. One knob for traditional tuning of power performance of CPU is the standard cell and embed memory SRAM, designed to achieve the power performance target. To meet CPU L1 cache SRAM performance requirement while minimizing the power consumption, three design options were explored. First, high density versus high current HC bit cell. Second one is 64-bit line BBL versus 32 BBL and standard threshold voltage VT versus low VT periphery resistor and design option trade-off. LVT are limited due to the impact of leakage power. HD with 64 BBL does not meet performance. So HD with 32 BBL or HD with 64 BBL is considered compared to HD 64 BBL. These have plus 19.3% and a plus 18.6 mode area respectively. As we can be the HD32 BBL has 3 higher performance and 9 lower power than HD65 BBL and hence is the topology used for CPU L1 caches for optimal power performance. The area costs up to food chain circuits, system, software, humanities. In any system, power performance trade-off made at higher level can make or break any improvement made at the lower levels. For example, if we low power knobs are made available at the circuit level are not correctly used at the system or software level, then the power overheads at a higher level cannot be optimized way by circuits innovation. Therefore, across optimization from circuits upwards are vitally important to the end product. The CPU software model utilizing a heterogeneous multiprocessor HMA architecture. In the mobile performing, there is a wide range of demand for high performance in burst modes, sustainable performance in a thermal limit, applications and low power modes for continuous usage. Thus, a heterogeneous multiprocessor architecture that includes both high performance and low power CPU in adapted to fit all the power performance profile needed. Since this architecture different than previous computing model of multiprocessor system, a new software model was needed. Let us see this picture. They are MEOL connections, MEOL connection. Thank you.